normal modes, we obtained the following equation of motion in the matrix form. In this notation, Q is n column, and matrices M and K are n by n symmetric matrices. This equation, written in the matrix form, will allow us to unleash linear algebra on this problem. We will look for a solution in the familiar form, namely that Q as a function of time will be the real part of a complex quantity Z, with Z now being not just a single number, but a column of numbers. We will write it as A times I omega t. Substituting this expression into our matrix equation, we will find minus omega squared times matrix M times column A E I omega t will be equal to matrix minus K times column A times E I omega t, which we write in the form of matrix K minus omega squared M times column A, and should be equal to 0. Note that omega squared is a scalar. Now, this equation is the standard eigenvalue problem in linear algebra. This is our n column, and this here is n by n matrix. How do we proceed to solve this standard eigenvalue problem? Well, first we can notice that if the determinant of the matrix K minus omega squared M is not equal to 0, then it means that an inverse of this matrix exists. And if we multiply the equation by this inverse, we're gonna simply get that A is equal to 0. Of course, that means that there are no oscillations. Clearly, this is not the answer we want. Therefore, we conclude that we require the determinant of this matrix K minus omega squared M to be equal to 0. Setting this determinant to 0 gives us n-degree polynomial, which will give us n roots of the scalar omega squared. Couple of things to note. We can prove that matrices M and K are both symmetric and positive definite, which means that for any non-zero vector Q, Q transposed times matrix M times Q will give us a positive quantity, a scalar. It is known from linear algebra that symmetric and positive definite matrices will guarantee to give us n independent roots with all of the values of those roots to be positive, even though some frequencies can be the same. Thus, we expect from this standard problem to get roots omega 1, omega 2, all the way to omega n, which will be eigenvalues. And we also expect to get I1, I2, all the way to In, which will be eigenvectors. Here my omegas are scalars and my a's are n-column vectors. In other words, we have that matrix K times eigenvector A I will be equal to eigenvalue omega I squared times matrix M times the eigenvector AI. Thus, the mode I can be written as Qi of time given by column AI times cosine omega it minus delta I. Delta I would be set by initial conditions. Another fact of linear algebra is that columns A1, A2 all the way to AN form complete set. In other words, we can decompose any solution of motion Q of t into the bases formed by these columns. In other words, general solution Q of t can be written as a sum of coefficients psi, which will be a function of time, times time-independent columns AI. The coefficients psi are known as normal coordinates, which oscillate independently from one another. Let's prove it. Our equation of motion in matrix form, and we substitute the expression for Q, and we get sum of psi double dot sub I m times A column corresponding to the ith mode, and that should be equal to the sum of psi's times matrix K times column AI, which, using the expression for eigenvalue, we can rewrite as minus sum of psi omega squared times m a column I. Remember that columns A form independent vectors. When we multiply them by matrix M, they will still be n independent vectors. Recall that independent vectors cannot be written as a linear combination of each other. In other words, the only way that this expression can be true is when this coefficient is equal to this coefficient with a minus sign. We have obtained the result that says that normal coordinates oscillate independent from each other, each at frequency given by the eigenvalue of our problem.